Hey everyone, welcome back to another study shed video. Today we're going to be doing a problem regarding the topic of series in calculus. This problem is question number 6 from the 2017 Calculus BC exam. Let's get started. Question number 6. A function f has derivatives of all orders for the x on the interval from -1 to 1. The derivatives of f satisfy the conditions where f of 0 equals 0, f prime of 0 equals 1, and the nth plus 1 derivative of f evaluated at 0 equals -n times the nth derivative of f evaluated at 0, for all n greater than or equal to 1. The Maclaurin series for f converges to f of x for absolute value of x less than 1. In part A, we want to show that the first four non-zero terms of the Maclaurin series for f are x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. And write the general term of the Maclaurin series for f. In part B, we want to determine whether the Maclaurin series described in part A converges absolutely, converges conditionally, or diverges at x equals 1, and we have to explain why we say so. In part C, we have to write the first four non-zero terms and the general term of the Maclaurin series for g of x, where g of x equals the integral from 0 to x of f of t dt. Finally, in part D, let p of n of half represent the nth degree Taylor polynomial for g about x equals 0 evaluated at x equals 1/2, where g is the function defined in part C. We have to use the alternating series error bound to show that the fourth degree Taylor polynomial evaluated at half gives an error less than 1 over 500. We broke part A into two parts. We first show the first four terms of the Maclaurin series, then we find the general term. Given the following information and the fact that the Maclaurin series is represented by the sum from n equals 0 to infinity of the nth derivative of x over n factorial times x to the n, we can find the coefficients of the first four terms of the series. All we need to do is plug in the values of n equals 2, 3, and 4 into the formula given above. We find that the second derivative evaluated at 0 equals -1, the third derivative equals 2, and the fourth derivative equals to -6. We can then write out the first five terms of the Maclaurin series, which has a highest degree of 4, matching the highest degree of the first four terms we want to find. After plugging in our known values, we can simplify to get x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the fourth, and so on. As seen, this can be rewritten and it matches what we want to find. Now we want to find the general term of the Maclaurin series for f. Looking at the terms, we can quickly note a pattern. If you don't really see this pattern, you can rewrite the series as x over 1 minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. We can assume that the nth term is raised to the nth power divided by n, yielding the following summation, the sum from n equals 1 to infinity of x to the n over n. However, we noticed in the series that the terms alternate between positive and negative. This means we have to include something of the kind of -1 to the n or -1 to the n plus 1. To decide which one is correct, simply plug in n equals 1 to both of them. -1 to the 1 gives us a negative value, and -1 to the second power gives us positive 1. So using this information, we know that we need to pick -1 to the n plus 1, since our series started with a positive value. Our final summation will be the sum from n equals 1 to infinity of -1 to the n plus 1 times x to the n divided by n. But wait! We need to make sure that our power series begins at an index of n equals 0, so we would have to translate everything appropriately. We get the summation from n equals 0 to infinity of -1 to the n times x to the n plus 1 divided by n plus 1. The question asks for the general term, so we can just take the term inside the summation, and that's our answer. Now for part B. Determine if the Maclaurin series written in part A converges conditionally, converges absolutely, or diverges at x equals 1. So the fact that we're being asked to determine conditional versus absolute convergence immediately should signify two things, the ratio test and the alternating series test. If you don't have a strong understanding of the series tests, then you should probably go check out our other video on the 10 different types of series tests. So moving on. If the series passes the ratio test, then it converges absolutely. If it fails the ratio test, then it diverges. If the ratio test is inconclusive, then we'll have to apply the alternating series test, and then we would know that it converges conditionally. We're given x equals 1, so we just immediately substitute that into our series. After simplifying, we get the summation from n equals 0 to infinity of -1 to the n over n plus 1. Your intuition should tell you that the series conditionally converges, because it's the alternating harmonic series. But we still have to show work, and we will do that using the ratio test. We'll apply the ratio test definition where the limit of n approaches infinity of absolute value of a of n plus 1 divided by a of n. We will evaluate this limit and we get the value of 1. So because the limit equals 1, we know that the ratio test is inconclusive, so we have to resort to the alternating series test now. The alternating series test has two conditions. The limit as n approaches infinity of a of n has to equal 0, and a of n plus 1 has to be less than or equal to a of n for all n greater than 0. So we first find that the limit as n approaches infinity of 1 over n plus 1 equals 0. In this case, a of n is just 1 over n plus 1. -1 to the n is not included in a of n. In the second condition, we find that 1 over n plus 2 is less than or equal to 1 over n plus 1. So the given series converges conditionally by the alternating series test. Finally, we have to test if it's absolutely convergent. All we have to do is take the absolute value of the series, and we get the summation from n equals 0 to infinity of 1 over n plus 1. We can use a limit comparison test for this because the given series resembles the sum from n equals 0 to infinity of 1 over n. The sum from n equals 0 to infinity of 1 over n diverges by the p-series test since p equals 1. Now we apply the limit comparison definition. Since limit of n approaches infinity of 1 over n plus 1 divided by 1 over n equals 1, we know that the given series diverges by the limit comparison test. Now we can write our concluding statement. Since the absolute value of the series doesn't converge, the given series converges conditionally at x equals 1. In part C, we want to write the first four non-zero terms and the general term for the Maclaurin polynomial for g, if g of x equals the integral from 0 to x of f of t dt. We already found f of x in part A, so all we need to do is replace x with t to find f of t. Because we want the first four terms and the general term of the integral of f of t, we write out the first four terms of f of t, and then we write out the general term of f of t. We would integrate this from 0 to x, and we would get the solution, where the integral from 0 to x of f of t dt equals x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20, and so on, and then the general form is -1 to the n times x to the n plus 2 over n plus 2 times n plus 1. Note that we can neglect the second part of the integral's answer by the fundamental theorem of calculus. Because the resulting function is only x's, if we plug in 0 to all of the x's, the value of integral effectively becomes 0, and adding 0 to the series doesn't do anything. Finally, we have part D. Let p of n of half denote the nth degree Taylor polynomial for g evaluated at x equals half. Show that the error in estimating the value of g of 1/2 using the 4th degree Taylor polynomial differs by less than 1 over 500. To aid our work, we need to write g of x as a series. G of x is the sum from n equals 0 to infinity of -1 to the n times x to the n plus 2 divided by n plus 2 times n plus 1. Because we're finding the nth degree Taylor polynomial for g evaluated at x equals half, we can plug in half into the summation. Notice that this is an alternating series, so we can use the alternating series error bound, which is the absolute value of the sum minus the nth partial sum is less than the nth plus 1 term of the sequence. Obviously, s equals g of 1/2, but what is the nth partial sum in this case? We are given that we want to find the error between g of x and the 4th degree Taylor polynomial, so our nth partial sum is the 4th degree polynomial. However, what n will produce this polynomial? Looking back at g of x, we see that if we plug in n equals 2 into g of x, we get a 4th degree term. Now we know that we need to subtract the second partial sum, n equals 2, from s. So by the alternating series remainder, we need to find the third term. To find the third term, simply just plug in n equals 3 into the g of 1/2 equation. Evaluating and simplifying our answer, we show that the remainder is 1 over 640, which is less than 1 over 500. So the error indeed is less than 1 over 500. And that concludes our video. Thank you all for watching, and we hope that you learned something new from this video. We'll be uploading new videos every Sunday. We hope to all see you next week. Happy studying!